In this lecture, we are going to discuss the Hamilton-Jacobi formalism and small oscillations. As from the previous knowledge, we know that h dash minus h, that is the new Hamiltonian minus the old Hamiltonian, is equal to dou f by dou t, where f is the generating function and the transformation is canonical. So for a canonical transformation, the h dash, that means the qp, it changes to capital Q and capital P. So a transformation from QP to capital Q, capital P, for canonical transformation, you have a generating function f is equal to Q, P and T. Okay, so now this is capital P, generating function f of Q, capital P and T. Now we can write f is equal to f of small q, capital P and T. Now let us write down what is df. That's equal to dou f by dou q into dq plus dou f by dou p into dp plus dou f by dou t into dt. Now I'm just dividing by dt, so what we are going to get is this equation, and now this we can rewrite it as dou f by dou q times q dot plus dou f by dou capital P times capital P dot plus dou f by dou t. Now so this is df by dt. That means the rate of change of the function f, the generating function, is given by this. Now in Hamilton-Jacobi theorem or Hamilton-Jacobi formalism, we have h dash as equal to 0. Now which implies, now let us take it down, that is from canonical transformations, we know that this, let it be in QP coordinates, and let here we have capital Q and capital P coordinates. Now here in the old system, we have Qi dot is equal to dou h by dou pi, and pi dot is equal to minus dou h by dou q. Alright, so that is qi dot and pi dot. And similarly for the new Hamiltonian, with respect to new Hamiltonian, we have qi dot is equal to dou h dash by dou p, and pi dot is equal to minus dou h by dou q. So this is what dou h dash by dou q. Now according to the in Hamilton-Jacobi formalism. So Hamilton-Jacobi formalism as we have h dash is equal to 0, and since h dash is equal to 0, qi dot is equal to 0 and pi dot is equal to 0, which means q and p are constants of motion. P are constants of motion. So this is what we make the conclusion out of this. Now what we are going to do is we are going to substitute pi dot in this equation, this one. Now here we have the equation df by dt is equal to dou f by dou q dot plus dou f by dou p, capital P into capital P dot, plus dou f by dou t. Now here we have this equation pi dot is equal to minus dou h by dou q, dou h dash by dou q, and this is equal to 0, and this is due to Jacobi Hamilton-Jacobi formalism, and we understood, and here this is also equal to 0, and so since this is equal to 0, we can write pi as constant of motion. Pi is constant of motion, and now this is now this value is being substituted here, so p dot is equal to 0. Now we can write df by dt is equal to dou f by dou q into q dot, plus now second term becomes 0, and now we have dou f by dou t. Now dou f by dou q, it is f with respect to present, which is means we are going to find out what is not there in the generating function. So generating function, we know that it is a function of f of q, capital P and t. So q is there, which is not present is small p. So what we are going to write here is small p. So that is small p q dot plus dou f by dou t, and that is nothing but df by dt. Now once again, so now let us write down what is dou f by dou t. From here, dou f by dou t is equal to df by dt minus q dot times p. Now q dot times p, and this dou f by dou t is nothing but h dash minus h. So df by dou f by dou t is nothing but h dash minus h, which is equal to dou f by dou t, and let us write down that is equal to dou f by dou t, and we know that h dash is equal to 0. Since h dash is equal to 0, we can write dou f by dou t equal to minus h. Now once again rewriting this equation, we have dou f by dou t, which is nothing but minus h dash, minus h is equal to df by dt minus q dot p. Now we need df by dt. Now rewriting this equation, we have df by dt equal to uh, minus h plus q dot p. So that is q dot p minus h. Now what about this q dot p minus h? This is nothing but the Lagrangian EL. So now we can write df by dt is equal to Lagrangian L, and f is nothing but integral L dt, Lagrangian L dt from time t1 to t2. So the generating function can also be written as the integral t1 to t2 L dt. Now the Hamilton-Jacobi equation of motion. So let's write down the Hamilton-Jacobi equation of motion. Now h dash minus h is equal to dou f by dou t. Now this implies dou f by dou t. Now this is h dash is equal to 0, dou f by dou t. Bringing this h to the right, we have h dou f by dou t plus h is equal to 0. Now this is the Hamilton-Jacobi equation, and what is p? P, small p, is equal to dou f by dou q, and let's write down this. P is equal to dou f by dou q, and whatever we have PR, if it is the radial, we can write dou f by dou r. Now just to imply it is Hamilton-Jacobi's equation, we will replace f with s. So rewriting the entire formula in terms of s, we can have the Hamilton-Jacobi equation of motion as, so writing the Hamilton-Jacobi equation, h dash minus h is equal to dou s by dou t, and h plus dou s by dou t equal to 0. So this is the Hamilton-Jacobi equation, and as we have written, p is equal to dou f by dou q. This can be written as dou s by dou q, and PR for the radial is equal to dou f by dou r equal to dou s by dou r. Coming to the small oscillation, we have so-called the angle of oscillation. When we are considering the simple pendulum, And now displacement, this is a linear displacement when we are considering the oscillator or spring mass system. So here this the angle of oscillation and displacement is very small. So in such cases we represent it as small oscillation. Now for simple pendulum, we have the potential V that's given. Let's draw the simple pendulum here. Here we have a fixed point. This is the bob, and this is the angle theta. Now V is equal to having the bob mass is equal to m, and the length of the simple pendulum as L. We can write V is equal to mg L into 1 minus cos theta. Now this is the potential. Now for a small angle, so theta is very small. So when theta is small, we can write two components, that is sin theta equal to theta and cos theta is equal to 1 minus theta square by 2 up to second order. So 1 minus theta square by 2, and here 1 minus cos theta we can write it as 1 minus of 1 minus theta square by 2. So 1 minus cos theta will be equal to theta square by 2. So you can replace sin theta by theta and 1 minus cos theta by theta square. So we can understand that V is equal to mgl into theta square by 2. Now through small oscillations, now we can understand the normal mode of vibration, normal modes of vibration. Now this vibration can be lattice vibration, or molecular vibration. Now the first derivative of the function dv by dx, that is the potential with respect to x, and for small oscillation v is the potential should be a function of the position. V of position is a position dependent variable. Now dv by dx, when you put it equal to 0, we get the value of x, for example x equal to a, and this particular value when you put it in d square v by dx square, this should give you a positive value, positive at dv square by dx square at x equal to a should be positive, and this positive value is called k, or wave number or wave vector, wave number or wave vector, and k is equal to m omega square. And what is the omega? Omega is the frequency of oscillation. Okay. Now coming to the frequency of oscillation, we have a secular equation secular equation for small oscillation that satisfies the equation v minus omega square times t, the magnitude. This is equal to 0, where v is the potential and t is the kinetic energy. Now this, when you incorporate in as the matrix, we can easily calculate the omega, which is frequency. For small oscillations, we have the characteristic equation or the secular equation. The characteristic equation is in terms of when we are writing it in the form of matrix. Now the secular equation v minus omega square t is equal to 0. So from here we can write v minus omega square t times x equal to 0. Now from here, if it is a 2 by 2 matrix, if it is a 2 by 2 matrix, we will have two eigenvectors when solving this equation. So x is equal to, we would get either x1, x2, either similar, which can be plus and plus some values we can write plus a plus b. Now this implies the oscillation is symmetric. Now this represents the 2 by 2 matrix represent the atoms. A, this is A atom, this is B atom, either A molecule or B molecule. Now this oscillates in the positive direction. Now this is what is meant by when you have both the values of this vector plus A and plus B. Now similarly we will also have another eigenvector which is x1, x2 equal to plus A and minus B. Now this is anti-symmetric oscillation. Anti-symmetric oscillation. So oscillation is anti-symmetric, which means one is in the A in the positive x direction while B oscillates backwards. That means in this direction. So this is anti-symmetric oscillation. Now this is what we are going to get from the solving the eigenvectors, and when you get the omega square, it gives you the frequency of oscillation. Frequency of oscillation, or it's nothing but d square v by dx square. Now this is nothing but the eigenvalue. Frequency of oscillation is nothing but the eigenvalue of this matrix 1. As we have learned, we have v minus omega square t is equal to 0. This is the secular equation. Now here in the secular equation, both v and t are matrices. V and t are matrices. Now here we are going to learn how to write the potential and the kinetic energy to be expressed as matrices. We are going to learn how we can express v and t in terms of matrices. Now we know that the kinetic energy will be written in the form of velocity. So t is a function of, let us write q1 dot, q2 dot, q3 dot, etc. Now this is one, and now we need the matrix quantity. For example, this is t is equal to t I j, and okay, so tij means t11, t12, t21, t22, etc. So this is a 2 by 2 matrix. So we need to find out each element of this matrix. So tij can be written as dou square t by dou xi dot, dou xi dot, dou xj dot. Now this is how we can write the element, the ith and jth element, ijth element of the matrix, kinetic energy matrix. Now we can write t11 as equal to dou square t by dou x1 dot, dou x2 dot. Now let us also write down how to write t12, that will be equal to dou square t divided by dou x1 dot, dou x1 dot, dou x2 dot. Now this is how we can write the kinetic energy. And we have to note here that Tij will be equal to Tji. Now this is because the matrix is symmetric. This matrix is symmetric matrix. Now let us see how to write the potential V. So V is a function of we know its coordinates, position. So q1, q2, q3, etc. Now Vij is equal to dou square V by dou qj, dou qi, dou qj. So this is how we can write the matrix. Now if we need v12, that will be dou square V by dou q1, dou q2. Now sorry, here we have dou x1 dot. Okay, no, this dou square t by dou x1 dot, dou x into dou x1 dot. Now this is nothing but dou square t by dou x1 dot square. Yeah. Now similarly, if you want here v11, that's equal to dou square V by dou q1 square. All right. This is for just for x. If you want in terms of q1 dot, you can write q1 dot here and q1 dot here, and t12 will be equal to dou square t by dou q1 dot, dou q2 dot. Okay, so that's here. And again, this V is also symmetric matrix. Remember, both kinetic energy matrix as well as the potential energy matrix V as symmetrics. That means Vij equal to Vji. To express the kinetic energy and potential energy in terms of matrices, let us take an example of the Lagrangian. L is equal to half m x1 dot square plus half m, let me write m1 x1 dot square plus half m2 x2 dot square minus of half k into x2 minus x1 whole square. So this is the Lagrangian. From here we can write the kinetic energy T is equal to half m x1 dot square plus half, sorry, here is we have m1 half m2 x2 dot squared. Now that's about this. Now let us consider writing the matrix. Here we have x1 dot x2 dot, sorry, x2 dot, here x1 dot x2 dot. Now x1 dot x1 dot square, and the coefficient of x1 dot square is half m1, so half times m1. Here x1 x2, there is no quantity called in terms of x1 dot x2 dot, so this is 0, and this is, since it is symmetric, here also we will have 0. Now half m2 is here because we have x2 double dot. Now here we have half m2 because x2 dot, so x2 dot square, we have the coefficient is equal to half m2. Now coming to the potential V. Now this is V is equal to, now this is Lagrangian is L is equal to T minus V. Whatever we have here is the potential half K into x2 square plus x1 square minus 2x1 x2. Now so we will write V over here. This is x1, this is x2, this is x1 x2. Now x1 squared, the coefficient is half k. Now x1 x2, we have x1 x2 here, and similarly x2 x1 is also here. So this is x1 x2, this is x2 x1. So coefficient of x1 x2 is 2. Similarly coefficient of x2 x1 is also 2, but we have only in total 2 x1 x2. So what we will do is we will put minus half k here. So here also we have 2, so we will divide because we have to give both of them equally. So here minus half k, and here also minus half k. Now this is because in order to avoid the repeated things, redundant, okay, redundancy. Now x2 x2, so this is x2 squared, so it's again half k. Now this is the matrix. Now this matrix can be simplified in the form, let us write down half outside, that's equal to m1 0 0 m2, and the potential energy, this is T, and potential energy V is equal to half k, and here we have 1 minus 1 minus 1 1. So this is the potential. As a practice work, you can consider doing this problem. Lagrangian is given to be half small m x 1 dot squared plus half capital M x 2 dot squared plus half small m x 3 dot squared. And this is the minus half k into half k into x2 minus x1 squared plus half k into x3 minus x2 squared plus half k into this is this much. So this is the Lagrangian given. So the first part is the kinetic energy and the second part is potential energy, and we are asked to find out V and T, kinetic energy, in terms of as matrices. That's the question for practice. Here we have a question where Lagrangian is given as L is equal to half q1 dot squared plus q2 dot squared minus half into 3q1 squared plus 3q2 squared plus 2q1 q2. Now this is the Lagrangian given. Now we need to write the kinetic energy and potential energy. So kinetic energy is equal to half q1 dot squared plus q2 dot squared. Now V is equal to half 3q1 squared plus 3q2 squared plus, let us write down q1 q2 plus q2 q1. Now T is equal to, so here we have q1 dot q2 dot q1 dot q2 dot. So that's half we have already here. So let's write down 1 0 0 and 1 because there is no q1 dot q2 dot term. So this is the kinetic energy. So let us write down it as half 1 0 0 1. So this is the kinetic energy term, and potential energy we have again q1 q2 q1 q2. So q1 squared, let's write down half here, 3 q1 q2 is 1, q2 q1 is again 1, q2 that is q2 squared, that is 3. So we have the potential is equal to half times 3 1 1 3. So that's again two matrices. Now applying the equation, secular equation, V minus omega square T is equal to 0. So V is this. So what you are going to get is 3 minus so just combine these two equations. So half is common in both, so 3 minus omega square, so omega square here, and 0, then here 1, then again 1 here, and 3 minus omega square. So the determinant of this should be equal to 0. Now from this equation, how to find out the determinant? 3 minus omega square, so multiply these two and subtract this. 3 minus omega square squared minus 1 equal to 0. Now finding out the solution. 3 minus omega squared equal to 1, which means 3 minus omega square equal to plus or minus 1. So if 3 minus omega square equal to plus 1 and 3 minus omega square equal to minus 1, so these two are the equations. So here when we take, it will become omega square equal to 2, and in this case omega square will become 4. So which means omega equal to either root 2 or 2. So omega equal to root 2 and 2. This is the frequency of oscillation. This is the frequency of oscillation, and we are derived from the Lagrangian. As a practice work, please consider doing this problem. The kinetic energy is given as half m x dot square plus y dot square plus z dot squared, and the potential V is equal to half m omega naught squared into 3x square plus 3y squared plus 2z square plus 2xy. So this is the kinetic energy and potential energy. We are asked to find out the frequency of oscillation. Another question. The kinetic energy is equal to half m q1 dot squared plus 2m q2 dot squared, and this is the kinetic energy, and potential energy is equal to k times 5 by 4 q1 squared plus 2q2 squared minus 2q1 q2. And here also we are asked to find out the frequency of oscillation. Frequency of oscillations, and if omega plus is highest frequency of oscillation and omega minus is the lowest frequency, find omega plus by omega minus. So this is also a question, part of this question.